Morning, everybody. Welcome back to Linear Algebra. Plan for today, we're going to do the rest of Standard 10, talking about determinants. I've got my usual office hours today tomorrow. Today at 11 and 1, tomorrow at 10 and 1. And we're going to have a quiz Friday over Standard 10. I did post Standard 10 problems on Canvas on, let's see, what was it, on Monday after class. So I encourage you to check those out, mostly just kind of practice finding and evaluating determinants. Any questions or comments before we get started for today? When given the choice between eternal bliss and a ham sandwich, which would a mathematician choose?
Same thing.
Oh, that would be coffee. For stereotypical, not me. No, the mathematician would choose ham sandwich every time. Because nothing is better than eternal bliss. But you know what's better than nothing? Ham sandwich. Alright, so last time we talked about how to find a determinant of an arbitrary n by n matrix. So given a matrix like this, the way you find a determinant is to go into Wolfram Alpha and type out this sort of, no, I'm just joking. Now, practically speaking, that's what you would do if you're a mathematician and it's bigger than like a 3 by 3 matrix because you've got better things to do than find determinants once you know how. But we had this idea last class of you go through and sort of do row or column expansion, where, for instance, here, you can take 1 times the 2 by 2 determinant of what you would get if you remove the row and column with 1 in it. So 5, 6, 8, 9. Minus 2 times determinant of 4, 6, 7, 9, if you remove the row and column with 2 in it. And then same with 3. 4, 5, 7, 8. And then you do some crisscross applesauce to find your 2 by 2 determinants. And we talked about how you could generalize that to 4 by 4, 5 by 5 determinants. We said you could do any row or column to find the determinant. By the way, fun fact, after stuttering so many times last class trying to say the determinant, in my 10 o'clock section after I met with you all, I kept a tally of how many times I stuttered saying the determinant. Came out to 10. I had to know for science. But that was kind of what was up. So last time, we talked about how you find the determinant of a matrix, kind of what's the computational process. Today I'm interested in getting into some theory of how do you actually show, or how do you actually prove, that a matrix A is invertible if and only if the determinant of A is non-zero. Because we talked a little bit yesterday, I gave you all, we did a little reminder of why that's true for 2 by 2 matrices. But we haven't actually showed that this result holds for 3 by 3, 4 by 4, 5 by 5, for an arbitrary square matrix, in other words. So our goal for today, kind of the main thing I want to do theory-wise in this standard, is to prove this fact. So to do that, we're actually going to have to talk about some standard 1 stuff today and go back to looking at our different types of elementary row operations. And specifically, what I'm interested in doing is to talk about if you start with the matrix A, you do an elementary row operation to it to get another matrix. How does the determinant change when you do an elementary row operation? So we had 3 of these things. Anybody remind me, what's one of our elementary row operations? Things you can do to a matrix to get it into reduced row echelon form that doesn't change, say, the solution set of the underlying system of equations. John?
Switch rows.
Swap rows. Yep, that's one of them. Henry, what's another one?
Add one row to another row.
Add one row to another row. not the order that we had them in class, but you know what? That's perfectly fine. Actually, what was the last one?
Multiply any row by a scalar.
By any scalar? There's one scalar in particular we said we don't want to multiply a row by.
0.
Yeah. Third one was multiply any row by a non-zero scalar. Okay, the reason why, like if I wanted to look for the solution set to x plus 2y equals 6, that would have the same solution set as if I multiplied both sides of this equation by the same non-zero constant, like 5. Like the same x and y that make x plus 2y equal to 6 are going to make 5x plus 10y equal to 30, right? If I multiply both sides of the equation by 0 to get 0x plus 0y is equal to 0, or 0 equals 0, does that have the same solution set as x plus 2y equals 6? I would say not. Literally any x and any y will make 0 equal 0, when only specific combinations of x's and y's will make x plus 2y equal 6, or 5x plus 10y equal to 30. So that's why you can't multiply both sides by a 0, or multiply a row by a 0 scalar. It has to be non-zero, or the solution set will very much change. So what I want to do is I want to talk about each of these 3 different types of elementary row operations and say, for each of these, if you performed one of these elementary row operations, what happens to the determinant? Because turns out we get some interesting things happening. If you were to multiply any row by a non-zero scalar r, what's going to turn out to be the case is the determinant will also multiply by r. If you swap any 2 rows, the determinant will become negative. You'll multiply your determinant by -1 if you swap 2 rows. And if you add one row to another row in your matrix, the most complicated one of all, it has the craziest effect on the determinant, which is no effect at all. So let's see if we can, let's write that out and actually go through and prove that. So this is going to be a lemma that we're going to use to kind of prove the A invertible if and only if determinant of A non-zero theorem. Where we're going to let A be an n by n matrix. And we're going to suppose B is the matrix found by performing an elementary row operation on A. And then based on which elementary row operation we have, yes?
What is a lemma?
What's a lemma? It's a, it's a sweet yellow fruit that you, or not sweet, sour yellow fruit that you can suck on. So the first thing lemma, good question. I think we've seen this like once or twice before, but it's been a while in this class. A lemma is basically a result that's kind of a stepping stone to prove another result. It's basically like a theorem where we don't care about that theorem so much for its own sake, but we care about it because it's going to be used to help us prove something more interesting. So in this case, this lemma is going to be a result that in and of itself isn't particularly exciting, but once we prove this lemma, we can use that to help us prove this more spicy result, that a matrix is invertible if and only if its determinant is non-zero. Does that make sense? Cool. So first one, I'm not going to use the order you all have. In fact, I need to use a specific order for this, because one of these relies on the other two. If B is obtained by multiplying a row of A by the scalar value r, then the determinant of B is going to be r times the determinant of A. Meaning if we took a matrix A and we just multiplied a single row by, say, 2, the net effect of that is going to be to double the determinant of A. The second one is if B is found by swapping 2 rows of A, then the determinant of B is going to be the negative of the determinant of A. So if we swap 2 rows, that will actually multiply your determinant by -1. And finally, if B is found by adding 1 row of A to another row, then the determinant of B will be equal to the determinant of A. In other words, adding 1 row of A to another row of A will not actually change the determinant in any way. Oh, that rhymed. That was cool. I love unintentional rhymes. Unintentional. So, any questions or comments about what we're trying to prove? So, let's start with number 1. I'm going to show that if we multiply a row of A by a scalar R, the whole determinant will multiply by A. So, prove 1. Let's say if expanding, doing cofactor expansion along row K gives us, all right, y'all ready for a super technical formula? I know this is going to have a lot of kind of like small nitpicky pieces, but bear with me. It won't be too bad, I hope. Determinant of A is A1 times the determinant of stuff plus minus A2 times the determinant of stuff plus plus A sub n times the determinant of stuff. What's going to happen if we take A and we multiply the kth row by the scalar R? So let's say we multiply the kth row by the scalar R in order to get the should I keep a tally for this class too? I think I'm at 2 already. What happens if we do the same thing after we've multiplied our row by R? Well, the determinant of B is going to be the same entry in A. So let's say A is going to be A1, A2, up through AN, and then more stuff. B is going to be the matrix where we have blah, 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 R times A1, R times A2, R times AN. R times AN makes it sound like I'm trying to say R. So I'll stop there. So what's going to change if we take the determinant, if we expand along the same row? Where if we expanded along our row in A, we're going to take A1 times determinant of what happens if you remove that row in that column, minus A2 times the determinant of what you get if you remove that row in that column, etc., going up through A sub n. Well, for B, you're going to have RA1 times the determinant of the same stuff that you have here, minus R times A2 times the determinant of the same stuff you would have here, plus R times A sub n times the determinant of the same stuff have right here. Because if we're only changing it from A to B, if the only difference is this one row, when we remove that row in that column to take the determinant of the remaining stuff, this stuff is not going to change at all if the only change from A to B is in this single row. So the only difference between the formula we would get for determinant of A versus determinant of B is going to be each of these terms that we use for our cofactor expansion is going to be multiplied by R. So we'll get R times A1 times determinant of stuff minus RA2 times determinant of stuff, and so on. What can we do with this equation?
You can factor out an R.
We can factor out an R. Each term has an R attached to it, so we could say that's going to be R times A1 times determinant of stuff minus A2 times determinant of stuff plus A sub n times determinant of stuff. And what do we know about this expression? Well, if the stuffs match up here, 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 etc., that's just R times determinant of A. Because this expression is the same as what we have up here. So as you can see, I was very sloppy in this proof. Technically, if you're writing a formal mathematical proof, you really shouldn't say things like stuff. You should say something about like, oh, the determinant of what's left if you remove that row in the corresponding column in the matrix A. And this proof gets super technical. I just wanted to avoid writing out all the details of it. When the main point is the stuff from A here to here is exactly the same, since going from A to B, only this row is changing. The other rows are not changing at all. Yeah, Eleanor?
So if we define stuff before we use it as what happens when you're
You could, yes, treat stuff like a variable thing. Then you could totally do that. I don't feel like defining my stuff, so to speak.
Also, it only works for odd rows.
Technically, yes. Well, no, not, well, okay, fine. If it's not, then, if it's an even row, then it's, you throw a minus sign in front of everything. And it still basically works. Here, how about this? Plus or minus, 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 plus or minus. There, now it works.
plus or minus minus
Yeah? Okay, look, I want to get through this three-part lemma. This is just a lemma before we get to the main result. Oh, please don't take me too bad. So, that gives us our first elementary row operation. We know multiplying a row by a non-zero scalar will have the net effect of multiplying the corresponding determinant by that scalar. So let's go on to the second. So for the second one, we need to show that if we swap two rows, the determinant gets multiplied by -1. For this one, again, if we wanted to do this thoroughly, we'd need to be kind of super technical. So I kind of want to more so illustrate this one with an example. So let's start off by saying, what happens if the two rows are consecutive? What ends up happening? So let's say, for instance, A is going to be the matrix. Let's go back to the 1, 2, 3, 4, 5, 6, 7, 8, 9 example for a second. If I wanted to expand along the first row of A, Abby, what would I have to do?
I'm not sure.
Say what?
I'm not sure.
You're not sure?
No.
Gadzooks. Phone a friend.
Can we hit
So you would take 1 times the remaining column and row that isn't eliminated in one's column and row, so 5, 6, 8, 9. And then minus 2 times 4, 6, 7, 9, plus 3 times 4, 5, 7, 8.
Yeah, that's all I was mainly looking for.
Okay, yeah, I knew how to do that one. I got it now.
Do you know?
Now I do.
Okay then, Abby.
Okay.
Let's say I've swapped, I'm gonna do this, ask you the same question, except now we're gonna swap the first 2 rows.
Okay.
What? That's not swapping the first 2 rows. I'm sorry, I'm already thinking till like 5 minutes from now, and I'm talking about what happens if we swap the first and third rows. Okay. No, that wasn't it. I'm a mathematician, I know what I'm doing at all times. Okay, Abby, laugh it up. I want to expand along this row now to find the determinant of B, where what I've done is I've swapped the first 2 rows. What's that going to give me?
That's gonna give you the same answer as above, except the pluses and the minuses will be switched.
Yeah, because here, the top row entries have a plus minus plus in your 3 by 3 matrix. Second row has a minus plus minus, right? So this would give us -1 times the determinant of 5, 6, 8, 9, plus 2 times the determinant of 4, 6, 7, 9, minus 3 times the determinant of 4, 5, 7, 8. I'm going to throw that as a stutter. It wasn't a stutter, but it was me making a fool of myself, so I'm going to count it in the same thing. John, what do you notice about these 2 expressions?
They are the exact same except for the positive and negative.
Yeah, the pluses have all swapped to minuses and vice versa. So in other words, that's the same as taking the negative determinant of A. So in other words, if you swap 2 consecutive rows like that, the same expression is always going to occur, where basically your pluses become minuses and vice versa. And no, this is not a proof. This is just kind of an example to help illustrate what happens. Mainly because, again, if I wanted to get super technical and general with the proof, it would just get super detailed and icky. And I'm less interested you understand all the details, and I'm more interested in seeing, do you understand the main idea of what's going on here? But sort of like when we swapped, no, because this was a different order. When we multiplied a row by a scalar, we basically end up with a sort of thing where the stuff that is the 2 by 2 determinants of what's left is not actually changing if we swap 2 rows. If we eliminate for 1 for instance, if we eliminate the row and the column with 1 in it here, we'll be left with 5, 6, 8, 9. But if we do the same thing here, we'll still have 5, 6, 8, 9. So all the individual 2 by 2 determinants stay the same. The only difference is we're going from a plus minus plus to a minus plus minus, and so the determinants are negatives of each other. That only works if we have 2 consecutive rows. So what happens if our rows aren't consecutive? So let's say, and here I'm going to be even lazier. Well, actually, no, I'm not going to be lazier. I'm going to be a little more general here. Let's say a determinant of A is the determinant of row 1, row 2, row 3. And let's say we swap that and go with determinant of B is row 3, row 2, row 1. I claim determinant of B should still be equal to the negative of the determinant of A. that it's not just so simple as the same argument, because row 1 here would still have a plus minus plus. Down here, it would also have a plus minus plus. Whereas row 1 and 3 have the same sort of sequence of pluses and minuses. So, how do we show that determinant of B is the negative of the determinant of A here? Eleanor?
Well, one observation that we can make is that the leftover
Mhm.
so the 2x2 determinants
Mhm.
are upside down.
They're upside down. Does that change anything?
Yes.
Makes
Because the main diagonals are now swapped.
Holy moly. So it would give you the negatives of all the individual 2x2s this time rather than these scalars up front. That's certainly one way you could think about it. Another observation you could make, what would happen, I'm going to start here, based on what we just did up front, if I were to start by swapping the first 2 rows, that would multiply the determinant by -1, right? So that would be the negative of determinant of what we get if we have row 2, row 1, row 3. Bless you, by the way, whoever teaches everything. What would happen then if I swapped these 2 rows? John, what would happen to the determinant?
You cancel out the negative.
Yeah, we technically get negative, negative, which would cancel out, become a positive determinant of row 2, row 3, row 1. And then, how about we swap these 2? Consecutive rows. Actually, what's that going to do to the overall determinant? Yeah, we're going to get another negative. So we'll have 3 negatives that simplify to a single negative determinant of row 3, row 2, row 1, which is the same as saying the negative of determinant of B. So the key idea here is if to swap 2 non-consecutive rows, you can just swap consecutive rows an odd number of times to make that happen. Elmar?
But then what if you have a 4x4? And you do it one at a time? Is that? Or is that, no, never mind, I see.
It becomes harder. Like if you wanted to swap rows 1 and 4 in a 4x4, you could swap 1 and 2, then 2 and 3, then 3 and 4, and then 1 and 2 again. It gets messy, but you can still do it an odd number of times. To swap 2 non-consecutive rows, you can swap consecutive rows an odd number of times. And if you swap if swapping consecutive rows means your determinant multiplies by -1, well, if you do that an odd number of times, if you multiply by -1 an odd number of times, the net effect is you've multiplied by -1 once. So that tells us that if you swap any 2 rows, whether they're consecutive or not, you can always, the overall determinant will always multiply by -1. Dr. Balls. Questions or comments about that? So a third one's probably the most interesting, which says if you add one row to another row, where are all my erasers? They're all here. If you add one row to another row, the determinant has no change at all. Oops, I'll erase that. I'll keep it over here. I'm not going to accidentally erase it there. So let's take a look-see at this one. So let's say that A is going to be, we can write it out as row 1, row 2, and we'll, for the sake of argument, let's suppose that we're adding k copies of row 1 to row 2, but otherwise these would be the same. Or no, A is this. And B is going to be taking row 2 and adding k copies of row 1 to it. So in other words, A and B are the same, but to get from A to B, we've taken k copies of one row, the top row, and added it to the second row. Well, it turns out there's some nice properties with determinants that we're not going to prove that says you can actually break this up into saying this is row 1, row 2, row n, plus k times row 1, row 1, row n. This comes from a property in the book that determinant is linear over individual row operations, which is a fancy way of saying determinants will break up nicely if you have individual rows like this. They don't work on the matrix as a whole, but they do work up over individual rows. Henry?
So, sorry. In that example, why isn't the second determinant just a row of zeros and then row 1 for the second row, and otherwise rows of zeros?
Well, it's going to turn out to come out to the same thing.
Oh, okay.
We're about to show that this determinant comes out to 0 every time.
Okay.
So this will actually give us back just this determinant, which is the determinant of A. So you notice here we have a determinant of a matrix where we have the same row repeated multiple times. And I claim, I'll write this over here as a little bit of a side argument. If your matrix has the same row multiple times, its determinant is automatically going to be 0. Let's write this as a side limit. If A has 2 of the same row, the determinant of A has to be 0. So why is that? This is kind of a slick proof. I really like this proof. So let's suppose A has 2 of the same row. So I'm going to let B be obtained by swapping the 2 identical rows of A. So like if the first 2 rows of A are the same, like what we have with that second matrix up there, we swap them. So instead of having row 1, row 3 up through row n, we'll have row 1, row 3 up through row n. So what's the net effect of doing that?
Become negative, like the positive and negatives instead.
Yeah, well, since we swapped 2 rows, according to what we did earlier, that means that the determinant of A has to be the negative of the determinant of B. Since we got from A to B by swapping 2 rows. But also, if we're swapping identical rows, then what's the difference between A and B? Elmore?
Well, it means that negative A also equals A.
You're skipping a step, but if you're swapping 2 identical rows, then you haven't changed anything,
Yeah.
right?
Yeah.
But since the rows were the same to begin with, swapping 2 identical things doesn't change anything. B and A are still the same matrix, which implies they should have the same determinant as well. And if A and B have the same determinant, and their determinants are also negatives of each other, because you got from one to the other by swapping two rows, what does that tell us? Well, it tells us that the determinant of A is equal to the negative of the determinant of A. And Ben, how many real numbers are there that are equal to the negatives of themselves?
Just 0,
0 and nothing else?
nothing else.
Indeed. Yeah. Because we can very quickly from here, we can add determinant of A to both sides to get 2 times the determinant of A is 0, divide both sides by 2. Determinant of A has to be 0. So if you have 2 of the same row, you could do this sort of cheeky little argument to say that by swapping the 2 rows, you haven't changed anything, so the determinant is the same. But you've also swapped 2 rows, so the determinant multiplies by -1. So the determinant of A has to be equal to its own negative, which implies that it had to be 0. So what does that tell us? Well, that tells us here, well, this is just the determinant of A again. This is going to be K times 0 by that side lemma. So we just get back the determinant of A in the end. I'll be honest, all 3 of these proofs were kind of sketchy in different ways to avoid kind of diving into the details of having to introduce individual matrix element notation and such. But the main idea I want to get across is kind of these 3 results of what happens. If you do an elementary row operation to A, you're either going to multiply by a non-zero scalar, the non-zero is going to be important. You're going to multiply by -1, the determinant of A, that is, or nothing will change. Questions or comments related to that? Alright, main theorem time. Which is, well, it's this result right here. So we have an n by n matrix A, and we're going to say A is invertible if and only if the determinant of A is non-zero. So what does that mean? So the way we're going to show this is we're going to talk about what happens if you start with a matrix, n by n matrix A, and you fully row reduce it. Put it in reduced row echelon form. So if I start with the matrix A, and I want to get to the reduced row echelon form of A, how do you get from A to the reduced row echelon form of A? What are the things you're allowed to do, in other words, to get from there to there? Man?
Elementary row operations.
Yeah, you could do elementary row operations to get there. And since we now know what elementary row operations does to the determinant, that's going to allow us to find a relationship between the determinant of A and the determinant of the reduced row echelon form of A. So what I'm going to say is, since row reducing A uses only elementary row operations, what does this imply? Well, let's suppose that to get from A to the reduced row echelon form of A, you have to do some number of these 3 operations. So let's say, for the sake of argument, that that involves multiplies rows of A by R sub I k times and swaps rows j times. So in other words, we're multiplying some row by R sub 1, another row by R sub 2, another row by R sub 3, etc., etc. And we're also going to be swapping rows some number of times. We're also going to be probably adding a bunch of copies of one row to another row, but that doesn't matter as far as the determinant is concerned. So what does that tell us then? Well, it's going to tell us that the reduced row echelon form of A should be -1 to the j times R1, R2, up through RK times the determinant of A. Because each time we multiply a row by one of these scalars, keeping in mind these scalars can't be 0, that means the overall determinant of A gets multiplied by that scalar. So if we multiply rows by scalars k times, we're going to have k of these scalars that we've multiplied the determinant of A by. And if we swap rows j times, well, that's going to have the net effect of each time you swap two rows, the determinant gets multiplied by -1, right? So if we swap rows j times, we'll be multiplying by -1 j times, which is the same as taking -1 to the j power. Here's the cool thing. Since none of these scalars are allowed to be 0, that we're multiplying A by, because we said for an elementary row operation, the scalars you multiply rows by can't be 0. We know none of these terms are going to be 0, which is going to tell us that the determinant of A should be equal to the determinant of the reduced row echelon form of A divided by -1 to the j times R1, R2, up through RK. So I'm just getting determinant of A in that equation by itself. So Dr. Erstel, what does this have to do with invertibility? Well, if A is invertible, what do we know about the reduced row echelon form of A? Henry?
It's the identity matrix.
Yeah. Then that tells us that the determinant of A should be equal to the determinant of the n by n identity matrix over -1 to the j, R1, R2, blah, 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 RK. And what's the determinant of the identity matrix? Elmer? Doesn't matter what the dimension of your matrix is, the identity matrix always has a determinant of 1. So it's going to give us 1 over -1 to the j times R1 times R2 up through R sub k. And what do we know about this lovely looking number?
It's not 0.
Well, -1 to any power is non-zero. R1, R2 through RK are non-zero. 1 is not equal to 0. So you have all these non-zero terms you're multiplying and dividing by. It's non-zero. Meaning if A is an invertible matrix, the determinant of A should come out to some number that may be ugly, it may be scary, it may be terrifying, but it will not be 0. So what if A is non-invertible? What do we know about the reduced row echelon form of a non-invertible matrix? Specifically, what's going to be the last row of the reduced row echelon form of a matrix that's not the identity matrix. Keep in mind, each row in a reduced row echelon form has to start with the leading one. Abby?
Could it just be like, oh, never mind. I see. I don't know.
Have more confidence in yourself, Abby. Come on. What were you going to say?
The last row in a reduced row echelon,
Mhm.
it's just gonna be like 0, 0, 0, 1, right?
Yeah, typically, if you have the identity matrix. But what if you don't have the identity matrix? Yes. John?
Well, I think you already said this, but we would still have a leading one, right?
I don't think we could.
So it would just be all zeros.
It would be a row of all zeros. And if we have a row of all zeros in our matrix, what's going to be the determinant of that matrix with a row of all zeros?
Oh, 0.
Because we could just cofactor expand along the row of all zeros and just get 0 times blah minus 0 times blah plus 0 times blah minus 0 times blah, etc., etc. It's going to be 0. So if A isn't invertible, we could say that the reduced row echelon form of A will have a row of all zeros. Which means the determinant of A is going to be, as we said before, determinant of reduced row echelon form of A over -1 to the j, R1, R2, up through R sub k, which is going to be 0 over a bunch of non-zero stuff, which in turn is going to be 0. And that is our proof. If A is invertible, determinant non-zero. If A is not invertible, determinant will be 0. So, Dr. Ursel, what was the point of that whole theorem, of that whole lemma we proved about what the different elementary row operations do to the determinant matrix? Turns out what the elementary row operations didn't really matter, other than the fact that if your matrix had a determinant that was non-zero to start, doing any elementary row operation will not make it 0. Because if you multiply by a non-zero scalar, that's not going to 0. If you multiply by -1, that's not going to 0. If you do nothing, that's not going to 0. So that was the real point of the lemma, was to show us that doing elementary row operations will never make non-zero determinants 0. But if the determinant was 0 to start, then doing elementary row operations aren't going to change that. Multiply 0 by any scalar, you get 0. Multiply 0 by -1, you get 0. Leave 0 as 0, you get 0. And so ultimately, in the end, that's going to give us our answer. Have a good day, everybody. I'll see you all on Friday. So on Friday, we're going to start our last major topic of the semester, eigenvalues and eigenvectors. Before we leave, though, I have a present for you. We've proven a lot of things about invertible matrices at this point. I thought I put together a little packet that basically kind of highlights 14 different equivalent conditions to saying your matrix is invertible. Yes, we are up to 14 now, if you kind of look through all the theorems and stuff that we've proven or just talked about throughout the semester. Sort of a fun little checklist. At the bottom of the list is what we just proved today. Matrix invertible with an only determinant. Alrighty, and with that, hope you all have a good one. I will see you all on Friday. So on Friday, just so you know for the quiz, I'm not going to ask you to prove or explain any of this theorem we did today. It's mainly going to be focusing on can you compute a determinant, and do you know what the determinant says about whether or not your matrix is invertible, which is if it's 0, it's not invertible, if it's non-zero, it is. So mostly a pretty computational quiz on Friday. Have a good one. Oh, eat your beef. Yeah, recess timeout. You just finished Pinkerton today class. Let me know when you want to come back.
It's more practical.
Hi, Liam.
which I like.
That's your calculator? Get in there. Did you leave it behind one day or something?
Yeah, I used to.
Probably, that was probably so. Take care. See you later.
That's better.
See you later. Here. Don't look at this. This is funny. We have a lemma and we have a side lemma.
Not lemons,
Say what?
not lemons.
Oh, you don't like sour things?
Yes, it's a lemon. That's a good idea. Instead of calling them
Yeah, I made
lemons,
that
you
joke
call
in my
them
last
lemons.
class. I'm improving. Last section I only made 5 stutters instead of 10 like your all's class on Monday.